In this week's experiment, you're going to be looking at a simulation that is hosted by the University of Colorado. So you're going to open up a web browser on your lab computer, like Firefox or Chrome, and then you want to open the website that's listed in your lab manual. I've already done that here, and your screen will look something like this. Now before you start, there's 3 things you want to change. So over here on the side, there's this little box, and the first thing you should do is turn on the grid. So that gives you grid lines here on the main part of the page. Second thing you want to do is turn off the electric field and then turn on values. And I'll explain why you do those 2 things in a moment. Now down here at the bottom, we've got positive charges that we could drag out onto the screen, and also negative charges, and also sensors. And the sensor shows you what direction and strength the electric field has at that point, where the sensor is located, due to the charges. And you can drag the sensor around and see how the electric field is affected by the charges you've put out. Now the reason why we don't have electric field selected here is that if I click this, it puts this sort of cloud of arrows on here. It's a little confusing. We don't want that. Instead, we're just going to use a sensor to look at the electric field, and you'll notice that there's some numbers on here. So one of them is the angle for the direction of the electric field, and the other one is the one we actually need, and that is the electric field strength at that point. And so that's why we have the values checked off. We don't get those numbers unless this is also selected. Now question 1 tells you that you want only a positive field. So I'm going to get rid of the -1 by just dragging it back into its bin. And they tell you to put the electric field just on one of the intersections on the grid lines. The field sensor, you're going to put 2 grid steps away. So if you look at this little legend down here, that's 1 meter away, but it's 2 grid steps on the page. So you put your sensor 2 grid steps over, and you look at the value you've got for the electric field strength. Now I want to just pause here a moment and explain what electric field is, because it's a bit of a strange concept. The electric field is basically a measure of how much force an electric charge located here would have felt. So if I had put a charge here instead of a sensor, how much force would it feel due to the other charge? Now the units listed here, volts per meter, if you break down volts into SI units, volts per meter actually is equivalent to newtons per coulomb. So 9.02 volts per meter is equal to 9.02 newtons per coulomb. In other words, if I put a 1 coulomb charge at this location, it would feel 9.02 newtons. So an electric field tells you how much force an electric charge would have felt if it was located there. So question 1D actually tells you to put your sensor here and look at it, but also put it in 3 other locations. So you want to go 2 grid steps up as well, and 2 grid steps over in the other direction, and 2 grid steps down. So do this as carefully as you can. But the question they're going to ask you is, what do you see with regard to both the electric field strength and the electric field's direction? So obviously as I move this around, the arrow changes its direction. You'll be looking at that. You're also going to want to look at the magnitudes. Do they change or not? In question 1E, they then ask you to move the sensor 2 meters over, so 4 grid steps away. And you record the field, and the question they ask you is, when you double the distance, by what factor does the magnitude of the electric field change? So is it twice as big, 4 times as big, half as big? Compare the value you got here to the one you got when it was half that distance away. Then they ask you to confirm this by moving the sensor 3 meters away, so that's 6 grid steps away. So again, you relocate it, you look at your magnitude, and you try and figure out the proportionality. Is it twice as big, half as big, 4 times as big? What happens when you go 3 times as far away? And if you're looking for a hint to try and figure out the logic here, look up the equation, either in your pre-lab or in your class notes, that relates electric field strength to the distance, r. Now there's several more things they have you do in question 1. So for example, they tell you to grab the sensor and move it to half the original distance. So 1 grid step over rather than 2 grid steps over. And again, compare the E field here to what you got at twice that distance. You'll also look at it 1 meter over and 1 meter up, so diagonal like this. And again, you'll be talking about the magnitude and the direction here relative to the first case. And finally, for the last part of question 1, they ask you to map the electric field for a positive charge. So what does that mean? Well, it means you grab your sensor and you move it to all different locations like you've been doing, and you want to draw in the arrows at a whole bunch of different locations and different angles. So maybe something like this. So you'll sketch the arrows for a bunch of different locations into your lab book, showing both the length of the arrow and its direction. And as I said, try and put a lot of the arrows on. And you do want to try and imply, with the positions that you've chosen, that when the sensor is farther away, the arrow gets smaller compared to when it's closer up. So make sure you put enough arrows in to show that. Going back to the simulation, in question 2, you return the positive charge to its bin, so grab this guy and drag him back, and then you're going to replace it with a negative charge. So you grab one of those and drag it onto your screen. Again, they want you to map out the electric field. So like before, you grab one sensor and you drag it all around and draw a bunch of different arrows in your book showing how the electric field direction and magnitude changes depending on where the sensor is located. So like before, you would draw a bunch of different arrows onto your diagram. In question 3a, they ask you to remove that negative charge again and put the positive one back. And then they want you to add a large number of field sensors all around your charge, like this. And then what they really want you to do in question 3a is to add a second positive charge. Specifically, you're going to add it 4 grid steps to the right of your first positive charge. So I grab a second positive charge, and I'm going to put it 4 grid steps to the right of my original electric charge. And then the question they ask you is, what happens to the electric field? So look at the arrows, both in terms of their angles and their magnitudes. Talk about what changed. And in question 3b, they want you to map out the electric field. So basically draw what you have here. Lots of different sensors in different locations showing the electric field arrows pointing in different directions with different magnitudes. However, there is one sensor position that they want you to have. I'll just move this to a slightly better location. They want you to put one sensor above and exactly between the 2 positive charges, like this. And so you want to map the electric field for the whole screen, but they are going to ask you some questions about this one sensor in this location. And the question they ask you about this one sensor is they say, explain why the electric field points straight up. Because we've got 2 charges here, and the sensor is located diagonally relative to both of them, and yet the electric field doesn't point at an angle, it points straight up. And why is that? As they hint in the question, you should use a vector argument for this. So you should think about the x and y components of the electric field due to this charge, and the x and y components of the electric field due to this charge, add those up, and then explain why the electric field at this point doesn't have any x components anymore. It's only got a vertical y component. In question 4, they want you to remove one of these positive charges and replace it with a negative charge instead. And again, you're going to map out the electric field. So grab your sensor, move it all around the screen, and draw in arrows for a variety of distances and angles. And then again, they do want you to put one sensor in one particular location when you do this, and that is right in between these 2, so like that. So you'll map out the electric field for the whole screen, but they're going to ask you questions about this one. And the question here is, why does the electric field right here point exactly sideways? Because we've got 2 charges, and the sensor's right between them, but the electric field doesn't go to 0. Instead, it points sideways. And why is that? Again, come up with a vector argument for why this happens. Now in question 9, they ask you to do something kind of interesting. They ask you to stack 8 more negative charges on top of this one. So you're going to have 9 in total, sitting in the same location. So I'll do that now. I've got 1 there already, and I'll go 2, 3, 4, 5, 6, 7, 8, and 9 in total. So I've got 9 times as much negative charge sitting here as I have positive charge sitting here. And they do want you to map out the electric field again, but you don't need a picture of it this time. So just grab one sensor and move it all around and have a look at what looks different this time. So we've got 9 times as much negative charge here as we had last time, and they just want you to look at the electric field and see how things have changed. So do that, but again, you don't need a picture in your book. Instead, you'll answer a question about this. Question 9b is kind of neat. There is one location, and one location only, on this screen where the electric field goes to 0. So not small, like what it does when you're far away from the charges, but actually 0. And it's not even very far away from the charges. So you hunt around and try and find the one spot where the electric field goes to 0. And when you find it, you should use a vector argument to explain why it goes to 0 at that one location. And then in question 6, you're going to calculate it mathematically and show that at that one location, somewhere on here, the electric field goes to 0. So not small, but actually 0. So questions 7, 8, and 9 are done in the lab manual only, so I'll jump over to that now. In questions 7 and 8, your group is going to be assigned one of the points on this diagram, and you have to calculate the electric field's magnitude and direction at that assigned point. The question tells you to assume that each of these grid steps is 1 meter long, so you figure out your distances r from that, and they also give you the value of k. You also know the strength of the charge, Q, right here. And then, as I say, you're going to calculate the electric field's magnitude at whatever point you've been assigned, and also figure out what direction the electric field is going to point from that assigned point. Question 8 is the same idea, but it's actually a much more involved calculation because there's 2 charges here. Again, your group is going to be assigned one of the points on the diagram, and you're going to need to do a vector addition of the 2 electric fields due to these 2 charges to figure out what the resultant's electric field's magnitude and direction are. So if, for example, this was your point, you would need to find the electric field's magnitude and direction due to this charge, this distance away, and then, separately, you'd also want to find the electric field's magnitude and direction for this charge at this other different distance away from your assigned point. So it's 2 completely separate electric field calculations to begin with. Then you have to do a vector addition of those 2 electric fields. So that would mean that you'd need to break those 2 electric fields for the 2 separate charges down into their x and y components, vectorially add the x and y components to each other, and then from those determine what the resultant electric field's magnitude and direction are at your assigned point. So as I said, it's quite a complicated calculation. If you're having trouble, call your lab instructor over for help. And there's also an optional help video on the website that is really helpful for doing this calculation. Now, the last question in the manual is not worth any marks, and some lab instructors don't do it, so your lab instructor may decide that as a class you're not going to do this one. But what this one is that all the groups in the class are going to put their results from the previous 2 questions on a Lycra sheet, which is a big stretchy fabric sheet. So you would use a protractor and a ruler and a special pen, and you would draw the arrow for the electric field that you calculated for that point to the right angle and the right length. So you would draw the electric field arrow on that sheet. And then, as a class, you stretch out the Lycra sheet, so you hold it tight, and your lab instructor will then put heavy balls on the sheet to mimic the electric charges. And then you can roll a ping pong ball from the point that you were assigned to check that the ping pong ball rolls in the direction of the electric field that you calculated. So you hold the sheet out horizontally, we put heavy masses on it to mimic the charges, and then you can put a ping pong ball at your assigned point, and it should roll in the same direction as the arrow you calculated for the electric field at that point. As I said, not every lab instructor will have you do this question, so your lab instructor will tell you whether or not you are.